So we are what we are looking at in algebraic geometry is trying to look at things which are which have an intrinsic meaning. Okay, so intrinsic means these are certain definitions and properties that you make or define which depend only on the object and not on other extraneous factors. So for example, what we are worried about is we are worried about varieties, alright, and then of course the varieties could be, they could be affine or quasi affine, or they could be projective, or they could be quasi projective. And when you say these things, you are trying to say that the variety is either sitting as an irreducible closed subset of some affine space or some projective space, or it is sitting as an open subset of such a set. Okay, so when we define variety, we are already thinking of it as sitting inside somewhere, either an affine space or a projective space. So there is this, and there is this fact that you are making it sit inside something which gives a certain ambiguity. Okay, because for example, if you take the line can sit inside any affine space in any way. Okay, so you can think of the line just as a A1. You can also think of it as one of the coordinate axes in A2, okay, or even any other line in A2, and you can also think of it as a line in 3 space A3. Okay, but in any case a line is a line. Okay, so what is intrinsic about the line is that it is a line, alright, and what is extrinsic about it is the way you are putting it inside. You are thinking of the line just as a line, or you are thinking of it as a line inside the plane A2, or you are thinking of it as a line in 3 space, which is A3, and so on. So these are, so what you must understand is that when we start working in algebraic geometry, start building the theory of varieties, we always start by embedding your object into some affine space or projective space. Even to define a variety, you have to think of it as sitting inside some affine space or projective space as an irreducible closed subset, or as an open subset, non-empty open subset of such an irreducible closed subset. But then finally what we want to really analyze and define and analyze and study is not I mean, we want to define and analyze and study only the properties which are intrinsic to the variety. We are not interested in they should depend only on the variety and not the way in which it is embedded. Okay, so the fact, for example, this saying that the line is one dimensional doesn't depend on whether the line is being thought of as a line A1, or whether it is being thought of as a line in A2, which is a plane, or whether it is thought of a line in 3 space A3. Whatever be the space in which you embed it, it's still one dimensional. So you see, we say that dimension is a very intrinsic property, because and in fact our definition of dimension, we have seen that we have given the definition of dimension in 2 ways. One is as a topological space. We have defined the dimensional variety to be topological dimension, and we also proved that this dimension is the same as if the variety is an affine variety, then it is the same as the Krull dimension of the affine coordinate ring of the variety. Okay, so the moral of the story is that the definition that the dimension is the topological dimension is a very intrinsic definition. It just depends on the topology of the variety, it does not depend on anything else. Okay, whereas the definition that that the dimension is the Krull dimension of the affine coordinate ring, namely the coordinate ring of polynomials on the variety. Okay, that ring, the Krull dimension of that ring is the dimension of the variety, is another definition, but that somehow seems to depend on that ring, because that ring it depends on the way in which the variety is embedded. Okay, if the affine variety is the affine variety could be embedded in so many affine spaces in so many ways as an irreducible closed subvariety, and in each of those cases you will get a coordinate ring, rings of polynomials. Okay, but thankfully for affine varieties we have seen that the coordinate ring itself is an invariant, it is an intrinsic thing, namely if you take two affine varieties then they are isomorphic if and only if their affine coordinate rings are the same. So which means that no matter in what way you embed the affine variety, the moment you say affine variety you are considering an affine variety is isomorphic to an irreducible closed subset of some affine space. It could be an irreducible closed subset in an affine space of any dimension. Okay, and the dimensions could be different, they are like the same line being embedded in a plane or being embedded in 3 space. Okay, so the ambient the bigger affine space in which your variety is embedded as a closed subvariety, that could be different, but still the ring of polynomials on that variety, the rings are all isomorphic, the affine coordinate rings are isomorphic. So we express this by saying that the affine coordinate ring is an intrinsic object that is defined connected with the variety. Okay, now so this is what I am trying to say, we are trying to it is very important that we begin by using extraneous or extrinsic things. Okay, but then finally we try to find out what are the things that are intrinsic. Okay, so in that list comes the affine coordinate ring of an affine variety, okay, which is intrinsic. Then of course the other thing that I introduced was the local ring at a point. The local ring at a point is something that is defined in a very intrinsic way. Okay, it is just defined using regular functions. Okay, and the point is that if you change the variety up to isomorphism, then the local ring will also change only up to isomorphism. Okay, namely if you have a variety and a point with an isomorphism carrying this variety to another variety and this point going to another point, then the local ring of the original variety at the given point is isomorphic to the local ring of the target variety, the isomorphic variety, at the image of the point that is gotten by the image of this point. Okay, so we say that the local ring is also something that is very intrinsic, namely if you change the variety up to isomorphism, the local ring will also change up to isomorphism. Okay, so what we are going to talk about, so in that direction I want to introduce another important ring associated with a variety. In fact this is not just a ring, it is a field, and it is called the function field of a variety. Okay, so I want to introduce that, and I want to tell you that I want to introduce it in a very intrinsic way and then show how to compute it for affine and projective varieties. Okay, so so let me put the title of the lecture as the function field of a variety, the function field of a variety, and so what is it that we are going to do? So the idea is very similar to looking at the way in which we got the local ring at a point. Okay, so what we did is see So we start with X, a variety, okay, and of course which means it's could be affine or quasi affine or projective or quasi projective, and we have a point, and then how do you define the local ring at a point of the variety. So normally what we did was if you have a point small x in capital X, then what we did is we defined O capital X small x, this is a local ring of X at X, to be O capital X small x tilde modulo an equivalence relation, okay. And how was this equivalence and what was this tilde O capital X small x tilde, these were just pairs of functions which were regular in some open in some Zariski open neighborhood of the point X. So this consisted of pairs of the form u comma f such that f is in OU and X belongs to U. So you are just looking at functions which are defined on an open neighborhood of the point X and which are regular, alright, and you took two such pairs, and then what is the equivalence relation. The equivalence relation was that two such pairs will be identified if they define the same function on the intersection, okay. So u1 comma f1 is equivalent to u2 comma f2 if well f1 restricted to u1 is equal to f2 u1 intersection u2 is equal to f2 restricted to u1 intersection u2, where of course we you have to remember that X is both in u1 and in u2. So X is in u1 intersection u2, so u1 intersection u2 is a non-empty open set, so it is in fact dense, okay, and you are just saying that f1 restricted to u1 intersection u2 is equal to f2 restricted to u1 intersection u2. In other words, these two functions can be glued together to give a bigger regular function on u1 union u2, okay. So in some sense, in the sense of complex analysis, we say that these are two function elements which are direct analytic continuations of each other, okay. So now of course you can weaken this condition. You could just say that f1 restricted to W is equal to f2 restricted to W, where W is an open neighborhood of the point X which is contained inside u1 intersection u2. That is also enough, because we have proved this and we keep using this all the time, that two regular functions if they are equal on a non-empty open subset, then they have to be equal everywhere, okay. This is true always, right. So so we got this local ring like this, alright, and of course we have seen that this how to compute this local ring, okay. We have seen how to compute this local ring and what it is in the affine case, what it is in the projective case, we have seen it, alright. But now what I am trying to say is, if you want the function field, it is very simple. What you do is you just remove this restriction of concentrating attention at a point, okay. Just do not worry about the point, and the beautiful thing is that you if you do not concentrate attention at a point, you go global, okay. You get something global. So what you do is put k x to be k x tilde to be the set of all pairs u comma f such that f belongs to OU, and now there is no restriction on u inside X as an open subset, open non-empty, okay. Of course here also whenever I say f belongs to OU, it is implicit, it is understood that U is an open subset of X, okay. So U is a Zariski open neighborhood, okay. Fine. So now you see, so what is the difference between this and this? The difference is that here you are only taking open neighborhoods of the point small x, but here you are simply taking any non-empty open set and you are taking a regular function on that, okay. So you just drop attention to a point and lo and behold what you get is you repeat the same procedure, what you get is not a local ring, you get a field, okay. So now what you do is again you define the same thing, you define same equivalence relation u1 comma f1 is equivalent to u2 comma f2 if and only if f1 restricted to u1 intersection u2 is equal to f2 restricted to u1 intersection u2. Of course for this I mean you need not require it on all of u1 intersection u2, it is enough to even require it on an open non-empty open subset of u1 intersection u2. And you must always remember that this very important fact that variety by definition or varieties are all irreducible, and therefore you take any non-empty open subset of a variety, it will continue to be irreducible, it will be dense, and any two non-empty open subsets of a variety will always intersect. Okay, so this is the problem of the Zariski topology. The problem is that the open sets are huge. Okay, they are dense, their closure is the whole variety. I mean of course non-empty open sets, they are huge, and any two of them will intersect, right. And well, so it is just enough to require that f1 and f2 coincide in an open subset of u1 intersection u2, okay, non-empty open subset of u1 intersection u2. So this definition, this equivalence is the same as equivalence here, only thing is you are not focusing attention at a point, alright, and then you put kx to be kx tilde mod the equivalence. Okay, so of course when I write mod equivalence I mean equivalence classes. Okay, so this is a set of equivalence classes, this is also a set of equivalence classes. Now the beautiful thing is that just like in this case the set of equivalence classes gave you a local ring. Okay, you got a commutative ring which is a local ring which had a unique maximal ideal which was represented by functions which are regular in a neighbourhood of x and which vanish at x. Okay, and in fact the representatives in the local ring, namely the equivalence classes, were called germs of functions. Okay, so this is the set of germs of regular functions at the point x, and every germ of a regular function is represented like this, it is represented by a regular function on an open neighbourhood of the point. Okay, now here we call the elements here well they are kind of they are called rational functions. Okay, they are called rational functions, and basically they are to be thought of as functions that are regular on an open set. Okay, that is how you should think of rational functions. Rational function is nothing but a regular function on an open set. It is not a regular function on the whole variety, but it is a regular function, it may be a regular function only on an open subset which may be a proper open subset. Okay, so that which means that there could be points where it is not regular. Okay, where you cannot think of, where you might extend the function but it may not be regular, right. So so let me write that down. Elements equivalence classes of kx are called rational functions. They are called rational functions, so they represent they are represented by a regular function on an open subset, alright. And further you see this kx, this is actually a field. Kx is a field, and why is that so? Because you take two elements in kx, so I have this map kx tilde to kx, this is a quotient map, it is a surjection, so that is why I am putting this double arrowhead, and this is a set of equivalence classes, this is mod equivalence. Okay, and what we are doing is you are taking, if you give me a rational function u1 comma f1, you send it to its equivalence class, which I will indicate by putting a square bracket. Okay, and well, if you give me another rational function u2 comma f2, I will send it to so rather let me use u comma f and v comma g. So this will go to b comma g round bracket followed by a square bracket, the square bracket indicating the equivalence class here. And then how do you add these two guys? It is very simple. You add them like this. You give me two rational functions, you just add them on their intersection, because as I told you, we keep always using the fact that any two non-empty open sets will intersect. So u and v will intersect on the intersection, both functions make sense, so I could add them. So I can do this, I can take this equivalence class and define this to be the sum, alright. And then the same way I could define product, I can put product here and I can put product here, okay. So depending on what your either sum or product can be defined like this. And now I want you to check, it's easy to check, as you must have done in this case, that this definition of addition and multiplication is independent of the choice of representatives, because I have defined the sum. When I define the sum of two rational functions, I am actually taking the sum of the representatives, and I am taking the sum of the representatives on the intersection of the domains where the representative functions are defined, okay. So and similarly when I do for the product, I also use representatives, but then whenever you use representatives, you have to make sure that your definition is correct, it is well defined, so you have to check, okay. So check that check well definedness, that is a simple exercise, that the same kind of exercise as you would have undergone for the case of a for the local ring. So this will make kx into a commutative ring. In fact you will have that kx is a commutative ring. Of course it will be commutative ring because addition of functions and multiplication of functions is pointwise, and that is commutative because the functions are taking values in the base field k, which is commutative, alright. So it is a commutative ring with one being the given by the pair x comma constant function 1 and 0 element given by the pair x comma constant function 0, okay. So it will be a commutative ring with unity and with this as 0 element, alright. And in fact not only that, it will in fact be a k algebra because a regular function multiplied by a scalar is also a regular function, because scalars are of course regular functions, they are thought of as constant regular functions, okay. So so kx is a k algebra. Of course in our discussion we always fix small k to be an algebraically closed field where we are working, that is where we are studying our varieties. So and this kx is a k algebra, okay. All functions take values in small k, all regular functions take values in small k, and well now the point is the following. The point is, well, in this case after you took, if you took open neighbourhoods of a point and then you define this equivalence, and when mod this equivalence, you got a local ring, you got a commutative ring which was also a small k algebra, but it was a maximal, it had only one maximal ideal, and therefore it became a local ring. But the point is, in this case you do not get the only maximal ideal you will get is 0, and so you will get a field. So why is this a field? To show that this is a field, I will have to tell you that every non-zero element here is invertible, okay. So if you take u comma f not equal to the 0 element, the 0 element is x comma 0 in kx, okay. So then what I want you to understand is that you see you take z of f, okay. See z of f inside x will be a closed subset, okay, So what I want you to understand is that whenever you take a variety and you take a regular function on it, okay, and you take the set of the locus where it vanishes, okay, that will always be a closed subset, okay. So in fact, you know, I should say it's a closed subset of U in fact, because f is defined only on U. I should not write x here, I should be careful, alright. So f is a regular function on U, and mind you, U itself is a variety. U is any open subset of a variety is again a variety, okay. So U itself is a variety, f is a regular function on U, okay, and if you take the 0 set of f, namely the set of points in U where f vanishes, that is going to be a closed subset of U, okay, because actually, you know, roughly the idea is that the closed subsets are defined by vanishing of polynomials, right, in the affine case. It's in the affine case they are common zeros of bunch of vanishing of a bunch of polynomials, and if you are in the projective case, then it is common zeros of a bunch of homogeneous polynomials, okay. In any case it is just vanishing of polynomials that gives the zero the closed subsets for the Zariski topology, and therefore if you take a regular function on a variety, U is also a variety and f is a regular function on that, then locally f is a quotient of polynomials, and therefore looking at zeros of this regular function is like looking at locally the zeros of the numerator polynomial, because locally f looks like a numerator polynomial divided by denominator polynomial, and the zeros of f will be just the zeros of the numerator polynomial, okay, and therefore essentially you are just looking at zeros of polynomials, and therefore again you are going to get a closed set, okay. So this is a closed subset, and mind you, z of f, you know, cannot be z of f cannot be U, okay. Z of f is not equal to U, because if z of f is U, that means f is identically 0 on U, but then if f is identically 0 on U, then f is equal to the 0 function which is identically 0 on x, and that will contradict the fact that these two are different elements of the function field, okay. So zf is not equal to U, because otherwise you will see that U comma f is the same as U comma 0, and this is equivalent to x comma 0, which is a contradiction, okay. So so I should say contradiction. It's a contradiction to the fact that these two are different, alright. So that means z of f is a proper closed subset of U, so its complement in U is again an open subset of U. So you know U minus z of f inside U is non-empty open, and of course, you know, where a regular function does not vanish, its reciprocal is also a regular function, okay. After all, a regular function is a locally of the form quotient of polynomials. Where it will not vanish is where the numerator polynomial does not vanish. If the numerator polynomial does not vanish, okay, already when you are writing the quotient, the denominator polynomial cannot vanish. If the numerator also does not vanish, then its reciprocal, the reciprocal of these two, numerator and denominator, will give you also a rational, will again give you a regular function at that point locally, okay. Therefore wherever a regular function does not vanish, its reciprocal is also a regular function. So what happens is that you will get this pair U minus zf, which is an open subset of U, proper, it is a non-empty open subset of U, mind you, this is actually, mind you, it is dense in X itself, okay. It is a non-empty open subset of U, and U is a non-empty open subset of X, so this is a non-empty open subset of X, so it is irreducible, it is dense, okay, it is a huge open set, okay, and on this I have the function 1 by f. 1 by f is certainly a regular function on that, okay. So this element, if you multiply it with the original element U comma f, what you will get is just x comma 1, you will get this, okay, by the definition of multiplication, alright, because after all 1 by f and f are going to multiply to give you 1 wherever f does not vanish, okay, and wherever f does not vanish is certainly a huge open set, alright. Therefore so what this tells you is that whenever U comma f is not the 0 element, mind you, this is the 0 element, this is a 0 element in Kx. So whenever something is not 0 it has a reciprocal, there is something with which you can multiply it to get 1, this is 1, this is the 0 in Kx and this is the 1 in Kx, okay. So here also when I write 1 equal to x comma 1 I mean this is the 1 in Kx and this is 0 in Kx, okay. So what I have proved is that every non-zero element is, I have a commutative ring in which every non-zero element is invertible, so it is a field. So the moral of the story is that Kx is a field and is a field extension of K, okay, because it is a K algebra. So you know it's an over ring of K, it contains small k as a subring, and whenever you have a larger ring which is a whenever you have a when you have a ring extension and both are fields, it is actually a field extension, okay. The smaller ring is K, it is a field, the larger one that we have defined and constructed is also a field, okay. This is a field extension, right. Now and this is called the function field, it is called the function field of x. Okay, it is called the function field of x, and what is so special about the function field of x? So the answer to that geometrically is the following, that the function field of x will give you all the information that is true on a large open subset of x, okay. So this is the philosophical importance, this Kx will contain all the information about x which you can find on a large open set. Of course any non-empty open set is large, okay. So you take any general open set in X and you take properties that are valid on a general open subset of X, then all those properties they will be captured by Kx, okay. So Kx geometrically captures what is happening on a large open set of X, okay. So Kx captures the geometry on a general geometry of okay. So the point is, you see what I want you to understand is, both in the local ring case and in the function field case you are just looking at pairs of functions, okay. You are just looking at pairs which consist of a regular function defined on an open set, okay. Here you are only concentrating on open sets which contain a given point and you get the local ring, and the local ring contains all the information in a neighbourhood of that point, okay. All information in a neighbourhood of that point, how the variety behaves in a neighbourhood of that point, all that information is controlled by this and captured by this, okay. Whereas if you want to know what is happening on a general open subset of X, that information is captured by Kx, okay. So this is a, if you want to study a general open subset of X, if you have a geometry question about a general open subset of X, okay, then what you have to study is this. If you have a question about what is happening at a point of X, then the object you have to study is this, the local ring, okay. So these are two extremes, okay, and I will tell you how they are connected, we are going to see how they are connected. Of course they are all connected to each other, and essentially they are all everything is done by commutative algebra, okay. So now comes the following question. So you can ask how are these things connected. So the first thing I want to tell you is that we have maps so before that yeah, we have maps, we have natural maps O OX OXX KX. Okay, there are maps like this. So what is this map? Let f be a regular function on x. You just send it to since f is a regular function of x, then I have the pair u x comma f, and its equivalence class will give me a point. It will give me an element of the local ring at this point x, because the elements of the local ring at a point are simply germs of regular functions defined on a neighborhood of the point, and since f is a global regular function, it is also a regular function at that point, so I can take its germ. So this is a germ of f at the point, and well, what I can do is, on the other hand, this is this map, alright. Mind you that I can also send a map from here to here, namely if you take u comma g, let me write v comma g. What is this v comma g? G is regular function on the open set V which contains a point x. Okay, this is the germ of V, this is the germ of G at the point small x. Okay, and of course G, this open set V may be a proper open set. G may not extend to a regular function on the whole of x. It may be restricted. It might just be defined on this open set. Okay. Now, but anything here, I can further send it to the same thing here. Mind you, I'm using the same notation, but the point is this equivalence is the equivalence in the local ring. This is the equivalence in the function field. Okay. Okay. So, but I'm using the same square bracket. Now, the point is that, of course, there is also a map which goes like this directly, and that is simply going all the way to x comma f, which is just the composition of these two maps. This will also go to x comma f, where again this square bracket is the equivalence class here, and this square bracket is the equivalence class here. Okay. Alright, so I have maps like this. Now the fact is that these maps are the fact is that these maps are injective K-algebra homomorphisms. Okay, so these are injective K-algebra homomorphisms. Okay, these are injective K-algebra homomorphisms. Okay, so of course they are K-algebra homomorphisms, namely they are ring homomorphisms which are K-linear. Okay, so that's no problem. It's very easy to see. The point is the injectivity. So the injectivity comes like this. You see, that's also something that uses again this fact that if two regular functions are equal on an open set, then they are equal everywhere. Okay, of course that open set has to be a non-empty open set, of course, because you need a point to test. You need points to test whether two functions are equal actually. Okay, so well, you can see why this is injective is very clear, because if x comma f is 0, okay, then it means that f vanishes in a neighborhood of small x. Okay, but that means f is equal to the 0 function in an open set containing small x. Okay, but then if you use the fact that two regular functions, if they are equal on a non-empty open set, they are equal throughout. So if small f vanishes in a neighborhood of small x, then it vanishes everywhere. That means this f itself is 0. Okay, so that will tell you why this is injective. And why is this injective? That's also literally the same argument. If you take a v comma g, germ of a function g which is regular in this open neighborhood V about the point small x, if it goes to 0 here, it means that it is equal to 0 on some non-empty open subset of V. Okay, but in any case that will also force it to be 0 everywhere. In fact, if this goes to 0 here, it will tell you that G is the 0 function on V. Okay, and the 0 function on V extends to the 0 function on x. Okay, and therefore this will itself be 0. alright. So the moral of the story is both these ring homomorphisms have 0 kernel, so they are injective ring homomorphisms. And what is the moral of the story? The moral of the story is the beautiful thing that regular functions sit inside the local rings, the local rings sit inside the function field. This is how the so the idea is that somehow when you are looking at it topologically, you have the whole variety X, you concentrate attention to a point, you get a larger ring, okay. If you have the whole variety X, you have OX, which is the regular functions on X, okay. Now you concentrate attention to a point, you get a larger ring, okay, that is a local ring at that point, okay, which is larger than the ring of regular functions. And then on the other hand, if you concentrate, instead of concentrating at a point, if you concentrate on an open set, you will get a much larger ring, which is in fact a field, and that is the field of rational functions. Now what I want you to understand is that in all these things nothing will change if I replaced X by an open subset U, okay. So in fact what will happen is that in fact if U is an open subset of X, is open and small x is in U, then we have a commutative diagram, we have equalities in fact OX to OXX. I mean at the level of local rings and at the level of function fields you are not going to have any difference. So so I'll put a hook arrow saying that you are considering this as subrings. What will happen is this will be the same as OUX is OU, and this will be the same as KU, and this will sit inside, okay. So if you the function field depends only on an open subset of X, so the function field of variety will not change if you replace X by an open subset. So Kx, the function field of X, if you replace X by U, non-empty open set, then Kx will be the same as Ku. By going to a non-empty open set you are not changing the function field, and that is just reflection of the fact that the function field captures information on a general open set. So if you go to a general open set the function field does not change, okay. And the local ring at a point also depends only on a neighbourhood of the point, it does not depend on the ambient variety. So whether you are considering X as a point of the open set U of capital X and calculating the local ring of small x of the variety U, or whether you are calculating this local ring of small x with respect to the bigger variety ambient variety capital X, you will get the same result, okay. So the local ring also depends only on a neighbourhood of the point, okay. And of course the fact and what's happening here is that you also get an inclusion like this, because every regular function on X can be restricted to give you a regular function on U, and these restrictions of functions, they are all injective because of the same old reason that if two regular functions coincide on an open subset, non-empty open subset, then they have to coincide everywhere. Or another way of saying it is if a regular function vanishes on an open subset, then it is identically 0, it will vanish on the whole variety. So you see this is what happens if you go to an open subset, and why these two are equal is something that you can easily get this equality in a very very easy way, namely what you do is and any element of Kx is of the form U comma f, where f is a regular function on U, and you take the equivalence class, and what do you have to do? It's very very simple. I should not use the same U, let me use V comma G, or even better let me use W comma H. W is an open subset of X, H is a regular function on W, then I have this pair W comma H and its equivalence class is the rational function here, okay. And what will I send it? It's very simple. You see W is a non-empty open subset of X, U is a non-empty open subset of X, so they intersect, so I can make sense of H also on the intersection, that's the element I am going to send it to. So I am simply going to send it to W intersection U comma H restricted to W intersection U, I take this class and then I take its equivalence class, and that is the element I am going to send it. In principle I should write this as a map, and you can see that this map will be a K algebra isomorphism, but then I put equality because actually as far as the functions are concerned, I am simply restricting the same function, so that is why I put equality there. Okay, if you think of them as functions, then you can put equality here and you can put equality here. Okay, so if you think of them really as functions. Okay, of course you have to remember that here you should think of representatives as functions on a non-empty open set. Okay, and here you must think of representatives as functions on a regular functions on a non-empty open set which contains the point small x. That is the only difference. Okay, so so you have this nice diagram, alright, and now what I have to do is to tell you what this kx will be if x is an affine variety, what this kx will be if x is a projective variety. Okay, we need to understand what that is. Okay, we have already understood what the local rings are when x is an affine variety or a projective variety. Okay, they are given by suitable localizations. Okay, we have to repeat this, extend this kind of argument to the function fields. Okay, so let me just state the result, then we will probably prove it in the next lecture. So here is theorem: if x is an affine variety, then kx is isomorphic to quotient field of Ax which is equal to Ox. Okay, so if x is an affine variety, then you know we have defined Ax, the affine coordinate ring of x, and we have proved that affine coordinate ring is equal to the ring of regular functions. Okay, and this equality being thought of as functions. Okay, we put this equality because we think of a function here also as defining a function there and conversely. Okay, and what if x is projective? If x is projective, then kx is well, let me put y so that I do not confuse. If y is projective, then ky is just, you take the homogeneous coordinate ring of y. Okay, the homogeneous coordinate ring is defined the same for a projective variety, is defined the same way as the affine coordinate ring is defined, namely you take the ring of polynomials of the ambient space that you are considering and then go modulo the ideal of functions that vanish on the variety. In this case, of course, you will have to take polynomial ring in of the affine space over the projective space in which this variety y is embedded, and go modulo the ideal of y, which will be a homogeneous ideal, and then you take this, and then you know what you do is you take the 0 ideal. Okay, that is a prime ideal, and this is localizing at 0, and then I will put another 0 here, saying that you are taking the degree 0 part of the homogeneous localization of Sy. Okay, so this is degree 0 part of the homogeneous localization. Sy at 0. Okay, so so here is the formula for the function field of an affine variety, and a nice formula for the function field of a projective variety. Okay, and you know, if you try to write out this kind of diagram, including the the local rings and the quotient fields, then what will happen is that you know, if you take O x small x, that is going to sit inside kx, and you know this kx is just Ax quotient field of Ax. Okay, Q represents the quotient field of Ax, that is Kx, that is what this first part of the theorem says. This is an isomorphism, and we have already seen that this is nothing but Ax localized at Mx, where Mx is the maximal ideal in Ax corresponding to functions that vanish at small x. So I should put small x here. So Mx is equal to ideal of functions vanishing at x. Okay, we have already proved this and we have this inclusion. Okay, and you must recall a fact from commutative algebra. It's very easy. If you have an integral domain, okay, then its quotient field will be the same as the quotient field of any of its localizations. Okay, the quotient field or field of fractions of an integral domain is the same as the quotient field or field of fractions of any of its localizations. In fact, the quotient field is the largest localization. Okay, it is a localization where you have inverted everything except the only element which you cannot invert, which is 0, and 0 is a prime ideal. Okay, and so you are localizing at the prime ideal. Okay, so this QAX is just Ax localized at the prime ideal 0. Okay, this is what it is. You are inverting everything outside 0, right, because localization at a prime ideal means invert everything outside the prime ideal. In this case, invert everything that is not 0, that will give you the quotient field. So this is the picture you get for the affine case. Okay, and you will get a similar picture for the projective case. If you take OYY, small y point of capital Y, where capital Y is a projective variety, this is going to sit inside ky, and what is going to happen is that the function field of ky will be just Sy localized at the prime 0 degree 0 part, and this will contain Sy localization at My and degree 0 part, where here My, so this is, of course this diagram commutes, this diagram commutes. This isomorphism of the local rings has already been proved. Okay, and it is this isomorphism of the function fields that I have to prove, and here again My is equal to all those ideal of homogeneous